Okay, so when you design a beam or any structure for that matter, we always anticipate the worst case scenario. It's like asking yourself, if my design will fail, saang parte ba ng design or saang parte ba ng structure yung unang bibigay? Now, as civil engineers, as future designers, you should always be able to ask yourself these questions, these critical questions, because only then, after determining the critical points, the critical sections of your design, of your structure, only then you can apply the appropriate engineering interventions that will prevent your structure from collapsing. Now, in the same manner for the beam, when you design a beam, you always base your design on the critical section. Okay? Now, for a beam, there are more than one critical section that is based on what type of failure you are looking at. But for this video, we'll just focus on the bending failure. So, for a beam, when you design a beam, as I have said, you always base your design on the critical section, and that's the section where the maximum moment occur. Now, in the same manner, when you analyze a beam naman, and by the way, designing and analyzing a beam are two different things. We'll explain it later as we go on with this topic. Okay, so when you analyze, and by analyze is, I mean to say is that you want to determine the capacity of the beam. You want to know how much moment can the beam carry before it finally collapses. So when you analyze, you tend to look at the most critical section of the beam. And yun na nga, yung sinasabi ko kanina pa, that's the section where the maximum moment occur. Because if your beam will fail, that's also the section where your beam will most likely fail first. Kaya yun yung tinatingnan natin. Now, this is the reason why in your strength of materials and even in your theory of structures, sandamakmak yung mga problems about determining the maximum moment and also the location of the maximum moment. So, ito yung rason kung bakit pinag-aralan nyo yun. Okay? So, I guess what I'm saying here is that when we design a beam, hindi yan kaya design lang, there are parameters that needs to be considered. And one of those parameter is, yun na nga, yung pinag-uusapan natin, yung bending moment. So for this video, we will discuss how bending moment dictates the design of your beam, or should I say, the dimension of your beam. But before anything else, if you are new to my channel, please don't forget to subscribe and hit the notification bell button below. So let me start by introducing this formula. This is the formula for flexural stress. This is the stress due to bending. That's why this is sometimes called as the bending stress. Okay? So the formula is FB is equal to MY over I. Okay, so first, una is yung FB. Now, on this course, you will be taught in two ways. You will be taught as the designers and you also be taught as investigators. Now, as designers, so pag sinabing designers, your duty is to design. Okay, so pag sinabing design, now there is no existing beam. You are just about to design pa lang. Pag sinabi namang as investigators, now there is an existing beam or an existing design of the beam and you want to investigate, you want to know the capacity of that beam. Okay, so pag sinabing FB, in the designer's perspective, that is the flexural strength. So a flexural strength, that is the property of the material to be used. And usually yung flexural strength is predetermined na yan. Parang you as a designers, dapat alam mo na before ka mag-design kung ano yung flexural strength ng material na gagamitin. So for example, kung concrete, dapat alam mo na kung ano yung compressive strength because the flexural strength of concrete is based on the compressive strength of the concrete. So I hope you learn this in your construction materials and testing. So sa pamamagitan ng experiments, malalaman natin kung ano ang different properties of the material. Okay, so on investigator's perspective naman, yung FB, that's the actual stress on the beam. So kung ano yung actual na nararanasan ng beam. Okay? Now, as civil engineers, dapat yung actual stress na nararanasan ng beam, dapat it should be lower than the flexural strength, than the capacity of the beam. Because, natural, if the actual stress will exceed the capacity of the beam, then your beam will fail talaga. Okay? So, dapat the actual stress is lower than the flexural strength or the capacity of the material to be used. Okay, and The second one naman is M. M is the magnitude of the moment that the beam needs to carry. So we will not discuss this into details na because you had this discussion in your strength of materials and even in your theory of structure. So M, that's actually the magnitude of the moment that the beam needs to carry. So yung moment yun. Okay, and of course, we also have the Y. Y naman, that's the distance from the fiber being analyzed from the neutral axis. So ano ba yung fiber na yan? Let us first discuss what is fiber. So pag sinabing fiber, say for example, meron tayong beam. Now at the neutral axis, we have there the what we call the neutral surface, and that's where the fiber wherein there is no stress at all. The fiber on that surface does not experience any stress at all. And the extreme most fiber naman, yung pinakataas or yung pinakababa na fiber, the extreme most fiber, dalawa yung pinaka-extreme natin ha. So, ang pinakataas at ang pinakababa, that's what we call the extreme most fiber, the extreme fiber. Now, if that fiber, if the beam deflects like this, now the uppermost fiber, the extrememost fiber at the top will be in compression and the extrememost fiber at the bottom will be in tension. Okay? So, pag sinabi nating fiber, when we think kasi of the beam, parang maraming fiber yan na pinagpatong-patong on top of the other. Okay? So, yung pinakataas na fiber, that's the extreme fiber in compression, at yung pinakababa naman na fiber, that's the fiber in tension. Okay? So, yung Y dyan is this distance. This distance. Okay? From the neutral surface or from the neutral axis to the fiber you are considering. So, kung anong fiber lang yung kino-consider. But as designers or as engineers, as designers, we always consider the extrememost fiber kasi yun yung fiber na pinaka na-stress. It could either be the extreme fiber in compression or it could either be the extreme fiber in tension. Okay? So, yun yung sinasabing fiber dyan. Okay, so next, we have I. I here is the moment of inertia of the cross-sectional area with respect to the neutral axis. The moment of inertia of the cross-sectional area with respect to the neutral axis. Okay, so kailangan ma-determine nyo muna yung neutral axis, then you find the moment of inertia with respect to that axis. Yun yung ibig sabihin ng I dito. Okay? Okay, so let us have an example. Okay, so for example, let's say for example, we have a beam of a span 5 meters. So may beam tayo, 5 meters yung span, and the beam is subjected to a uniformly distributed load with a magnitude of, say for example, 10 kilonewton per meter. And also, let's say yung gamitin natin na material is a wood, a lumber with, say for example, flexural strength FB equal to 10.3 megapascal. So we already determined the flexural strength of the material to be used as the beam, and it was found out that the flexural strength is 10.3 megapascal. Okay, so we will find the dimension of the beam. What should be the dimension of the beam? Okay, so first, dapat malaman muna natin kung ano-ano yung mga reactions. So we have here the reaction. Since this is just a uniformly distributed load, the beam is only subjected to a uniformly distributed load 10 kilonewton per meter, then we can easily find the reactions, and it was found out to be 25 kilonewton at both supports. Okay? Of course, na-determine na natin yung reaction, and for us to be able to design this beam, diba? As I have said earlier, our design will be based on the section where the maximum moment occur. Okay? So we need to find the maximum moment. And since this beam is only subjected to a uniformly distributed load, uniformly distributed lang naman siya, so we can immediately know that the section where the maximum moment occur is at the midspan kasi uniformly distributed lang naman siya, diba? So for sure, nasa midspan yung maximum moment. So we will pass a cutting plane at the midspan like this, and we will isolate from the cutting plane to the left of the beam. So we have here the cutting plane, and we isolate the left of the beam. So, okay, this is the beam, and also we have here the 10 kilonewton per meter, and also the reaction, which is equal to 25 kilonewton, and this distance is equal to 2.5 meters. Okay, and we need to find the moment here. Okay, so the reactive moment. Now, to find for the moment, we will sum the moment at the cutting plane here. We will sum the moment at the cutting plane here, and we will arrive at this equation. So the moment, that is equal to 25 multiplied by 2.5 minus the uniformly distributed load, which is 10, times 2.5 times 2.5 over 2. And simplifying this equation further, we will get 31.25, that is in kilonewton meter. So this is the magnitude of the moment, of the reactive moment at the cutting plane. And this is also the maximum moment. Okay? Next step is we will now determine the dimension of the beam, of this beam. Now take note, this is in rectangular form, and we will use the formula, the flexural formula, FB is equal to my over I. Okay. Now, based on this on this figure, we know naman that the centroid of this section is here. And the axis that passes through the centroid is what we call the neutral axis. Okay? And that's the axis also where the neutral surface passes through. The fiber where the neutral axis is located. Okay, as I have shown you earlier. Now, the height of the beam, we call it the depth the depth of the beam. And we also have here the width of the beam denoted by B. Now, we need to know what is the dimension of this beam. Now, when you design a beam in real life in real life situation, when you design a beam, you always see to it that your design is parang like this, parang mas mahaba yung depth niya kaysa width, dapat ganun at hindi ganito. Okay? Because if your design is like this one, then your beam will be subjected to parang prone siya to excessive deflection. So ang ginagamit natin, instead we use this one, dapat yung design mo is like this one. Okay? So we, as much as possible, we try to avoid that. Now, for the purpose of this discussion, we will use 0.4 as the ratio of the width to height. Okay, so we will use this ratio as the 0.4 as the ratio of B to the depth, width to the depth of the Okay, so now in real life situation, you as the engineer, ikaw yung bahala kung ano yung ratio ng width to depth. Okay? Basta, yun nga yung sinasabi ko, we try to avoid this type of cross-section. Dapat mas mahaba yung depth, mas malaki yung depth niya kaysa width ng beam. Okay? Okay. And also, there are researches kung ano yung pinaka-optimum na ratio ng width to the depth. Okay? So, you can search that on the internet for your reference. Okay, but for this discussion, we'll just use this ratio. So, using this ratio, we can then say that the width of the beam is equal to 0.4 of the depth of the beam. Okay? So, this equation is based from this one. Okay, so we will use this one. Okay, to connect, this is our formula. So we already have the value of FB. Our FB is equal to 10.3 megapascal. And by the way, megapascal is equal to Newton per mm squared. Yeah. So dapat yung moment, this is in Newton also mm. Okay? Para we have a consistent units. Okay, so for FB, we have here 10.3. This is in megapascal. Take note, this is in Newton, square mm. This is equal to, now our moment, we already determined the maximum moment, and that is 31.25 kilonewton meters. So for this to be in Newton mm, we just need to multiply this 31.25 by 10 raised to 6. Okay, so I will put it here. We have 31.25 times 10 raised to 6. This is in Newton mm. So this is your moment. And also your y, okay. Sinabi natin kanina, yung y dito, okay, yung y dito, itong y na to, that is the distance from the neutral axis to the fiber you are considering. Okay, for example, di ba, sinabi ko kanina, when you think of a beam, parang marami ang mga fiber na pinagpatong-patong. Okay, so may fiber dito, may fiber dyan, and so on. Maraming fiber yan, fiber na pinagpatong-patong. Okay, so for example, if you are considering this fiber, if you are trying to find the stress of that fiber, of this particular fiber, then yung y dyan is this one. Okay, yan yung y na gagamitin. The distance of the fiber you are considering, you are trying to find the stress, the fiber of which you are trying to find the stress to the neutral axis. Okay, so the distance is the y. Now, since we are nagde-design naman tayo ng beam, yung kino-consider nating fiber is the most stressed fiber. And that is the extreme most fiber. So, ano yung mga extreme most fiber? Diba? As I have shown you earlier, ang extreme most fiber is the fiber at the top and at the bottom. Yun yung pinaka-extreme most fiber. Yun yung fiber na pinaka-na-stress. Okay? Of all the fibers in the beam, yun yung fiber na pinaka-na-stress. Okay, so yung gagamitin mo is this distance. Okay? Yan yung distance. Anyway, kahit saang fiber yung gamitin mo, yung extreme most fiber at the top or yung extreme most fiber at the bottom, pareho lang ang distance niya from the neutral axis. That is for rectangular beam. Okay? For rectangular beam, pareho lang yung distance niya because the neutral axis can be found at the sa pinakagitna ng cross-sectional area ng beam. Okay, so ang gagamitin natin na y dito is this distance. Okay. Now, to denote that is the maximum value of y, diba? That's the maximum value of y. Take note how y is the distance from the neutral axis to the fiber you are considering. And we are considering the extreme most fiber. Okay, so instead na to denote na yun yung maximum value ng y, instead na we use y, we'll use the letter C. C yung ginagamit natin to indicate, pag C na yung ginamit, that indicates that you are actually considering the extreme most fiber. So kung nagdi-design ka, this equation will be FB, this is equal to MC over I. Kaya sometimes, yung nakikita natin is C instead of Y. Okay? So, pag ginamit yung C, ang ibig sabihin niyan, you are considering the extreme most fiber. Yun yung fiber na pinaka-na-stress. Okay? So, we will use the C and that is equal to, take note ha, your D here is this distance. Okay, so it follows that this distance is equal to D over 2, di ba? This is D over 2 and that is actually the value of C. So yung C natin is equal to D over 2. Okay, we will put it here. This is D over 2, yan, over yung I naman natin, since this is just rectangular lang naman siya. Let me erase this. Rectangular lang naman siya. So yung natin, yung moment of inertia at the neutral axis for a rectangular cross-section that is given by the base, diba? The base natin is B times the height, which is D for depth, cube over 12. So that is the formula for the moment of inertia with respect to the neutral axis of a rectangular cross-section. Okay, so as you can see, dalawa yung unknown natin. We have B, D. Yes, you have B and D. Dalawa yung unknown natin. But you can express one variable in terms of the other because of this equation right here. Diba? You can express B in terms of D using this equation. So, instead of using B, let me rewrite this one. This is 10.3 Newton per mm. Hindi ko na isusulat yung unit. We have 31.25 times 10 raised to 6. Okay, times D over 2 all over the value of B is 0.4 D. Okay, so we'll put it here 0.4 D times D cube. D times D cube, that is D raised to 4. Okay, so ano ko na lang, D times D cube, that is D raised to 4. D raised to 4 over 12. So this is your new equation. Now you can easily find the value of D. Now using your calculator, the value of D, wala nang space. Let me put it here. Let me erase this one. Okay, so we have here, this is our working equation. Okay, so our value for D is equal to, using your calculator, that would be equal to 357.027. This is in millimeters, of course. And the value naman for B, and take note that our B is equal to 0.4 of D, the depth. So, substituting this value here, makukuha natin ang value ng width natin, and that is equal to, this is 142.81 mm. We have here the dimension. We have here the depth and the width of the beam. Okay, so we have here 357.027 for the depth and 142.81 mm for the width. Okay, so this is our value for the depth and the width of the ano. Okay, so this is our beam. Now, saan ba diyan papasok yung yung tinatawag natin na reinforced concrete design? Now, before we go to that, okay, let's think about this first. Okay. If you want to draw what we call the stress diagram for the beam, now it would look like this. Okay, let me extend that. Okay, so ang stress diagram ng beam na to, ng cross section na to, it would look like this. Okay, so parang ganito yun yung itsura. Okay, so we have here the maximum stress in compression, and we have here the maximum stress in tension. So in compression dito, and this is in tension. So ibig sabihin, okay, if we consider this this fiber, may corresponding may corresponding stress siya. Now take note that our stress is a function of y. And take note that the y is the distance from the neutral axis to the fiber you are considering. Okay, so kung itong fiber yung kino-consider mo, ang makukuha mong stress is this one. Okay. If you consider this fiber, the extrememost fiber, ang makukuha mong stress is this one. Okay? And we already did that, and that's the stress 10.3 megapascal. This is actually the flexural strength. Okay? So yun yung capacity. So sinagad natin, that's the capacity of the material used as a beam. Okay. Now, if you are considering the fiber in the neutral axis, take note, an iya stress is 0. That is because your y here, take note, y is 0. So kung 0 based on your equation, in your formula, kung 0 yung y, of course, the value of your stress, of your FB is also 0. Take note that stress is a function of y. So as the y goes higher, yung stress mo is, it also increases. Okay? Same here, if you consider this fiber, of course, ang makukuha mong stress is this stress. Okay? Which is actually the same. Ang stress na to at ang stress here are actually the same. Diba? Because your y also, this y and this y is actually also the same. And that is denoted actually by C. Take note, we use C to denote that we are considering the extreme-most fiber. Okay? It could either be in tension or it could either be in compression. So for rectangular beam, the that distance in compression and in tension, they are just equal. Okay, so no need to worry for rectangular beam. Now, this stress diagram, this one, from the neutral axis pakadto habaw-baw, the stress diagram there, the stress that the beam is experiencing is in compression. This region here, ang stress na naranasan diyan ng beam is in compression. And in this region naman, ang stress na nararanasan ng beam dyan is in tension. That's why we have this diagram. So, sa pinakataas here, yung stress dyan is compression. That's why we have here the negative sign, negative 10.3. This stress, itong line na to, that is negative 10.3. And it was actually the flexural strength of the material used. Also, in here also, this fiber here, the extreme-most fiber in tension, of course, ang naranasan din niyang stress is 10.3 but positive siya because in tension. Okay? So, that is this is the stress diagram for this beam. Okay, now, this stress diagram, it can be represented by a single force. So, let us focus muna dito. This stress here, it can be represented by a single force. Now, we will call that force as C. We will denote the force that represent this stress diagram as C, capital letter C. Not to be confused with this C, ha? So, ang C na to is small letter C, that's the distance from the neutral axis to the extreme-most fiber. And C naman here to denote compression, okay? So, the stress in compression, it can be represented by a single force, C. We will call that force as C. And this stress naman, this stress in tension, it can also be represented by a single force. We will call the force T. Okay? So, paano ba natin malalaman yung magnitude ng T at C? Okay. So, yung magnitude ng T at C is actually because this stress here is, if you look at it in 3D, parang ganito yan. Okay, so we have here the C and the T. Okay, so this is the neutral axis and the distance from the neutral axis to the extreme-most fiber is C. We have here the 10.3 megapascal and we have here the positive 10.3 megapascal. So, paano natin malalaman yung magnitude ng T at ang magnitude ng C? Simply lang, we just need to find the volume of this stress diagram. 'Di ba? Triangular prism siya. So, we can determine the magnitude of the C just by solving for the volume of this prism, of the stress diagram, which is in a form of prism kung iti-3D natin. Okay? So, we have here the value of C. So, itong C, that is the volume of this prism. Since the base is triangular, so masasabi natin, the formula for triangular shape is 1/2 multiplied by the base, and the base is 10.3. So, this one here, this is 10.3 multiplied by C, and that is 178.514. Paano nakuha yung 178.514? Alam naman natin ang distance na to, di ba? The height of the beam, the depth of the beam, alam naman natin yung depth ng beam. You just divide it by 2 para makuha natin yung distance na to, which is equal to C, di ba? And that is 178.514. Okay, this is just the area of this one. Area pa lang yan. Volume man. So, we need to multiply pa this distance, in the distance. And that distance is equal to, you have here, yung width, yung base, the width of the cross section. And that is equal to 142.812 mm. So, multiplying this one, we'll get C is equal to negative, because negative here, negative 131,293.798 Newton. In Newton siya. So, if I will convert this into kilonewton, we'll have negative 131.294 kilonewton. This is the value of C. This is the value of this C here. Now, since pareho lang naman sila, ang pagkakaiba lang nila is yung yung direction nila, then we can immediately solve for T, that is actually positive 131.29 kilonewton. So this is our value for C and T. Okay, so going back to the 2D version, so ito yung 2D natin. So we have here the C, that is 131.294. Yung T naman is also 131.294 but positive siya to denote na tension. Okay? Now, since pareho lang naman yung magnitude nila, this C and T, so they have the same magnitude but they are oppositely directed. So clearly, naka-form tayo ng couple. 'Di ba? Couple yung tawag dun sa two forces with the same magnitude, oppositely directed and has a distance separated by a certain distance, then we have a couple. Okay? And the magnitude of a couple is just equal to ano ba? The magnitude of the force multiplied by the distance between the two forces. Okay, so yun yung magnitude ng couple. Okay. So we just need to use the magnitude of the force, and since pareho lang naman ang magnitude nila 131.294, never mind the negative, never mind the positive because it just indicate the direction of the force. And we also need to multiply it by the distance between the two forces and this distance. That is this distance. So we can easily find that distance, 'di ba? So we can easily find that distance since okay. This distance here, ito yung distance na to from here to here, that's actually equal to C, 'di ba? Or should I say 357.028 divided by 2. 'Di ba? That is this distance. Since this is triangular, alam naman natin kung saan yung centroid ng triangle, that is this distance is actually equal to 1/3 of C, 'di ba? Since this is C. So kung 1/3 dito, ini naman nga distance from here to here, that is 2/3 of C. 'Di ba? 2/3 of C. Same here from here to here, that is also 2/3 of C. 'Di ba? 2/3 of C. So 2/3 of C plus 2/3 of C, or should I say na lang, okay. Since this distance is this distance is equal to depth, 'di ba? The depth of the beam. O this distance is naman, this is 2/3 of the depth. Yan. So the distance between the two forces, the couple, is 2/3 of the depth. So if I were to find the magnitude of the couple, I'll just take the magnitude of the force, multiply it by their distance, and that is equal to 2/3 of the depth. Okay, so I can put it here. The couple is equal to, we have here the magnitude, never mind the sign, 131.294. This is in kilonewton multiplied by 2/3 of D, and D is equal to 357.027. Okay, so the couple then is equal to, oops, what happened? Couple. Okay, and this is equal to 31,250.33. This is in this is in kilonewton, and since this is in mm, diba, 357.027, that is in mm right here, naka-mm siya, so this is in kilonewton mm. Converting mm to meter, so we'll just divide this by 1,000, so the couple is equal to 31.25 kilonewton meter. So this is the magnitude of the couple. This is actually a moment, diba? 31.25. And notice that the magnitude of the couple is exactly the same with the moment that the section is experiencing, diba? This section is subjected to a moment of magnitude 31.25 kilonewton meter. At naka-form siya ng couple with the same magnitude, 31.25 kilonewton meter. So what does this tell you? O, ibig sabihin, yung 31.25 kilonewton, this is the applied load. So this is the magnitude of the moment that the section is experiencing. So nakaka-experience ang section ng 31.25 kilonewton meter. Then what will happen now is that the fibers on that section will react, 'di ba? Magre-react siya. So ang reaction niya is ito na, this stress diagram, which can be represented by these forces C and T, 'di ba? And that reactions, that forces, nakaka-form siya ng couple. Wala siyang net force because they are of the same magnitude. Walang net force because they are of the same magnitude and they are oppositely directed. So if you sum the forces, yung sum lang niya is 0. So walang net force. Since naka-form siya ng couple, meron siyang moment na nakikreate, 'di ba? May moment na nakikreate of the same magnitude, 31.25. So ibig sabihin, ang moment na experience ng beam ng section is being countered, parang ginka-counter siya ng couple. Okay? Parang may reaction na nangyayari diyan. Okay, so that is what is happening. Okay, so now for the case of the concrete naman, sabi kasi sa mga studies, mga experiments na kinandak ng mga different scientists and engineers, sabi doon, nalaman nila na ang concrete daw is very strong in compression but very weak in tension. So ano ang ibig sabihin niyan? If you use a concrete here, this T here will not exist because nga yung concrete is very weak in tension. Hindi niya kayang masustain yung T na to, yung 131.294 kilonewton here. So anong ginawa ng mga scientists? Anong ginawa ng mga engineers? So ang ginawa nila, since very weak man and concrete in tension, so to compensate this force here, naglalagay tayo ng bar. Ano yung bar na yan? Yung reinforcing bar. Naglalagay tayo ng steel. That steel there, itong this steel bar, that is to compensate what the concrete is lacking. Dahil weak kasi yung concrete in tension. Fortunately, yung steel bar na to is very strong in tension. Very strong in compression din naman siya, but yun nga lang, very expensive siya. So we just use parang reinforcing bar lang yung ginagamit natin instead of replacing this whole area by steel. Okay, so that would be very expensive. Okay, so to compensate what the concrete is lacking, naglalagay tayo ng Naglalagay tayo ng what we call that is the reinforcing bar. That's why we have this course. We call this course as the reinforced concrete design. Okay. So on the next topic, on the next video, we will discuss how we design a reinforced concrete beam. Okay, so that would be on the next video. So yun, I guess this is the introduction for the course Reinforced Concrete Design. I hope you learned something on this video. Please don't forget to subscribe and hit the notification bell button below to help me grow this channel. Okay? Thank you for watching.